All right, I want to talk a little bit about doing some resonance structures today. We talked about resonance structures in class on Wednesday, and I know you're working hard on daily problems for Friday, so I want to go over just some examples of how to do resonance structures so that we're happy about some of the problems that you're working on, and I think these tips will be helpful. All right, so let's do some examples. So first, let's look at delocalization of charge in molecules containing atoms other than carbon and hydrogen. So, delocalization of charge in molecules containing atoms other than C and H, and these things are called heteroatoms. All right, and so I want to just look at the examples I left you with at the end of class on Wednesday and see if we can work through them, because I think they'll help as you think about what you're doing for the problems on Friday. Sorry, the phone's ringing. All right, so let's first look at the anion. All right, so this is the carbanion that I left you with. All right, and so let's look at how we would delocalize this compound, or delocalize the charge in this compound. So like we talked about, first thing you should do is fill in all the CH bonds. Again, just to help you in your molecular accounting not to violate any octet rules. Right? We can add the lone pair on the oxygen as well. Right? And again, when we're thinking about delocalization of negative charge, we want to push the charge and the electrons away from that carbon towards a pi bond. Right? So we can do that here. These electrons will go towards the pi bond, and then this pi bond will turn into a lone pair on the other carbon. Right? So we can draw that out. Again, fill in the CH's so you just don't make any mistakes. Alright, and so you now have delocalized that charge over two atoms. And if you look here, you can see we're next to another pi bond on the C double bond O. So we can delocalize further. All right, and again, every time we delocalize a negative charge like this, we're going to go from lone pair pi bond, move that to make pi bond lone pair. All right, so we're always going to have 4 electrons moving between the structures. So we've been able to delocalize this charge over 3 different atoms, right? And another thing that's interesting when you look at different resonance structures that are not symmetrical, where you don't have the charge on the same atom, is to look and see which atom is most stable with that charge, which resonance structure is most stable. So if we look, we have negative charge on carbon, negative charge on carbon, negative charge on oxygen. Clearly oxygen is more electronegative, so this is the most stable contributor. Right? And then it's also important that we draw out what the resonance hybrid looks like. So again, draw in the sigma bond framework. And then you can draw in all the partial bonds, partial pi bonds, and partial charges. So we have partial pi bonds in those positions, and we have partial negative charge on oxygen, partial negative charge on 2 carbons. Okay? And since this is the most stable contributor, we could say that this is the largest partial negative charge. All right? And the other thing to be clear about, we talked about how if you're going to have resonance delocalization, all the atoms participating in resonance must be sp2 hybridized. So just to be clear, all of these atoms that are participating in the resonance delocalization are sp2. hybridized. So they all have a p orbital, and the p orbital is what enables the lone pair and pi bonds to participate in delocalization. All right. Let's look at the cation that I left you with. All right, so that was the cation that I wanted you to look at delocalizing that charge. Again, fill in the H's so we don't make any mistakes. Right, and now we have a carbocation. It wants electrons to move toward it, so we can move the pi bonding electrons toward the carbocation to stabilize it. So we've delocalized that positive charge over 2 atoms. And if we look, you can see that the oxygen has a lone pair immediately adjacent to the carbocation. So those electrons can also participate in charge delocalization. And now the oxygen is positively charged. So these are the 3 atoms over which we can delocalize that charge. And usually when we talk about this, and we think about what we did up here, the most stable contributor, most times people tell me, this is a horrible resonance structure. We have a positive charge in oxygen, oxygen's electronegative, so that one must not be that significant. Right? It turns out that this is the most stable contributor. Right? And so I think that's a really important point, right? In that I want you to think about why this would be the most stable contributor, right? Because that's critical for us to understand what's going on and how these sorts of molecules are going to behave, right? Because we're going to see a lot of them. So I want you to think about that. We'll talk about in class why that's the most stable contributor, right? And when we think about the hybrid for this one, again, we have the delocalization over all of those atoms, right? And we have delta plus, delta plus, delta plus. So the charge is shared over 3 different atoms, right? And it's very important, again, to recognize that all of these atoms that are participating in delocalization are sp2 hybridized. And so that when we think about how this molecule is going to behave, right, we can think about that oxygen and where the lone pairs are, right? And it's critical for us to realize that in this molecule, we have 1 lone pair in a p orbital so that it can participate in resonance delocalization, right? So that's very, very important for us to understand how this is working, okay? So that's all I wanted to say about charged molecules. I do want to say a little bit about neutral molecules to help you with the problems relating to benzene. All right? So I'll erase this and then we'll move on to that. All right, so when you're looking at neutral molecules, again, we're focused on how these molecules are going to behave, and we want to see which atoms are electron poor, which atoms are electron rich. And in problem number 1, you have a couple of problems that deal with substituted benzenes, right? And I want to talk just a little bit about that, right? The first point about benzene, just so that we're entirely clear, is that benzene is an amazing molecule, right? And you can draw 2 resonance structures for benzene that highlight that benzene is a completely delocalized pi system. There's only one type of pi bond in benzene, right? These, again, are the unicorn and the dragon. This is the rhinoceros. This is how benzene exists, all right? What we're doing in problem number 1, though, is looking at benzene, a substituted benzene, and seeing how that exists and how it behaves versus benzene itself. Is the ring in those problems, in those molecules, more electron rich or electron poor based on the substituents that are coming off of the ring? Right? So let me just do an example that's similar but different than what you're doing on the homework, right? Which is, if we have this molecule, right, so a carbon double bond nitrogen attached to the ring, how is this going to behave? Right? And when we look at these neutral molecules, look for pi bonds that are between two atoms of differing electronegativity. Right? So we would focus on the carbon-nitrogen double bond. Right? And so since nitrogen's more electronegative, the pi bond can shift up onto the nitrogen. So that's going to put a negative charge on nitrogen, positive charge on carbon. And again, just to be clear, this initial structure is going to be mainly how this molecule behaves. Let's say, for example, 90% of its character is going to be neutral. But there's going to be some fraction, let's say 10%, in which the charge separation is going to be important. It's going to help us predict how this molecule is going to behave. So now we can do some resonance delocalization. All right? And again, let's focus on that cation. The carbocation is very unstable, and let's focus on delocalizing that charge. So that now brings the positive charge into the ring, and we can delocalize that charge around the ring. Right, and you'll note when you do delocalization around a benzene ring that the charge is going to go on every other atom. Right, and we can draw one more structure here just to get back to what we started with originally. Okay, and again, we've shown that the positive charge is now delocalized throughout the ring, spread over 3 of the atoms in the ring. All right, and then if we looked at what the resonance hybrid would look like, we'd have delocalization over all of those positions, partial negative charge on nitrogen, partial positive on every other carbon. And the key point now is that if we compare this molecule to benzene itself, we can see that this molecule is going to be electron poor. And that's going to have important implications for how this molecule will behave. All right, so this is electron poor versus benzene. All right, and so when you're doing these problems, try to figure out whether the benzene ring is electron poor or electron rich based on the substituent that's attached to the ring. And we'll talk more about this in class tomorrow.